All right. So on behalf of my Indiana counterpart, Hans Schmitz, and myself, I'm Dwayne Friend with Illinois Extension. We want to welcome you to this webinar that we have as part of our Illinois-Indiana Climate Webinar Series. We did have a really good registration for this, really happy to see that. And I'm going to give an introduction to our speaker and then let her do her presentation. So I'd like to introduce Dr. Francina Dominguez. And Dr. Dominguez is hydroclimatologist. Her work is focused on the interactions between the land and atmosphere, and more specifically on changes in hydrology and climate due to human modification of the land surface and greenhouse gas emissions. Francina's two primary lines of research look at land-atmosphere interaction from two perspectives. One is the effect of climate variability and change, primarily extreme events, on surface hydrology, and the second one is the effect of changes in surface hydrology on climate. So with that, Francina, welcome, and I will turn it over to you.
Thank you, and thank you very much for the invitation. I'm very glad to be here. So today, well, first of all, I wanted to say just a plug to the new name of our department, which is Department of Climate, Meteorology, and Atmospheric Sciences, or CLIMAS. It used to be called the Department of Atmospheric Sciences. And today I'm going to talk about parts of the IPCC report, the Intergovernmental Panel on Climate Change 6th Assessment Report. And when I was asked by Dwayne to do this talk about the IPCC, I said, okay, I haven't read all of it, but I've read the parts of it, particularly those that relate to water. So that's what I'm going to be talking today about with you today. Okay. And so there are 3 working groups, and I'm going to be focusing on working group 1 results, which is the physical science basis. And within this, I will show you bits and pieces of chapters 2, 8, and 11. And chapter 2 is based on observations. Chapter 8 is water cycle changes, and chapter 11 is related to weather and climate extremes. And I will also be showing you some results from the summary for policymakers and the technical summary. So again, this is only a fraction of the report. This is working group 1 report. Okay, so let's just start kind of with the basics. There's a lot of chatter here, 1 second. Okay, so the main conclusion, the big conclusion is that the influence that we as humans have had on global temperatures is unprecedented in more than 2,000 years. The graph here on the left shows temperature anomalies relative to the 1850-1900 period. And remember, there are observations, our direct observations only go back about 150 years. So that would be this black line that you see here. All the rest here, the gray, are reconstructions using paleoproxy data, whether that be tree rings or ice cores. So these are all reconstructions, and this black part is directly observed. So here clearly you see, so this would be 2,000 years that our warming is unprecedented for this time. And this multi-century period has been the warmest in more than 100,000 years. We can go back even further with other paleoproxies, and we see that this period is the warmest. So this includes glacial and interglacial periods. Another thing that we can know from this report is that based on our state-of-the-art knowledge about using global climate models that incorporate all of this state-of-the-art knowledge, we are really good now at reproducing the observations. So observations, again, here in black, and the brown are the simulations that include everything, greenhouse gas forcing, volcanoes, solar variability, everything, and we're able to really nicely reconstruct those observations. If we remove the greenhouse gas forcing, and we only have natural solar volcanic activity, our temperature reconstructions look like this green curve here. So we are unable to reproduce the observed variability if we don't include greenhouse gas forcing, okay? And so that's the other kind of big conclusion that we have here. This is something new in the sixth IPCC report with respect to the fifth, which is that right off the bat in the summary for policymakers, we have the how much humans have contributed to the warming. So this is the observed warming that I just showed you, and we have that we've warmed about 1 degree above the 1850-1900 pre-industrial. And they break it out into how much of that warming is related to well-mixed greenhouse gases. So it's about 1.5 degrees. So we would already be at the 1.5 mark were it not for other human drivers that I am going to expand on here to the right. So we can further break down the well-mixed greenhouse gases into CO2, methane, nitrous oxide, halogenated gases, etc. And those are all have this positive effect. So they're warming the climate. However, there are other factors such as aerosols, and here the big one is sulfur dioxide that has a cooling effect on climate. So aerosols have cooled climate and have offset this greenhouse gas forcing. So that's we would be much warmer than we are right now, if it not for the fact that we're also polluting the environment. Okay, so this is a little bit of a busy slide, but I just wanted to before I begin the presentation in earnest, I wanted to talk a little bit about the language of the IPCC. IPCC uses 2 metrics to communicate the degree of certainty in key findings. So there's very precise meaning. So when the authors of the IPCC, their job is basically to read the literature corresponding to their region and evaluate what evidence is available. And then they have to make an assessment of whether there is robust evidence and if there is agreement among these different types of evidences. And they make a qualitative assessment about the confidence, going from very high confidence to very low confidence in a result. After that qualitative assessment, then there's a second step, which is quantitative, and that pertains more to the uncertainty in the finding expressed probabilistically. So here you go from virtually certain, which is 99 to 100% outcome probability, to exceptionally unlikely, 0 to 1. So one is like a qualitative and another one is a quantitative assessment, but they mean very precise things. And the authors of this report go under intense training to be able to do this. And I do want to say something tangential, which is that these authors are working pro bono, and it takes on the order of 3 years to do one of these. So it's a very intense process, and there's very kind of rigorous metrics when they're talking about the results of the literature. Okay, so I want to divide this into 2 parts. One is observations, so what has happened in the past, and the other one is projections into the future. I'm going to start off with observations. So as I said before, we know this, the world is warming. On the left, you see two maps. One goes from the 1900s to 1980s, and then you have the bottom here, 1981 to 2020. So you see the geographical distribution of the heating. Everywhere you see an X is that the trend is non-significant, sorry, and these are trends in degrees Celsius per decade. Anything red is positive trend, anything blue is negative trend. And on the right-hand side, we have averages over the world. Red is over the land and blue is over the oceans. So we see clearly that the land is warming more than the oceans. Down here, we have different data sets, which are basically all showing the same thing. And these bars are decadal averages. And what we see here is that each of the last 4 decades has been warmer than any decade preceding it since the 1850s. Let's look at this map, and you see a couple of things. You do see the land warming more than the ocean. You also see that it gets redder and redder at higher latitudes. So the Arctic is warming much, much faster than, say, tropical oceans. Okay, so this is the main result of the IPCC. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. So essentially the scientific community is certain about this. And if you read previous assessment reports, the language has gotten more and more certain. There's just much more certainty as you progress in time about this particular result. And of course, not only has it gotten warmer, but there's many other influences that this warming has had on other parts of the system. So here we see trends in specific humidity. So how much water is in the atmosphere? Green is more, brown is less. So increasing trend in green and decreasing in brown. Again, X means that the trend is not significant. And here I want to pause for a minute and talk about observations. So because we're talking about observations, if there are regions that are not well observed, like parts in Africa or like the Amazon forest or the ocean, you won't have a result. So there's blanks because we're just not observing. And so in many cases, even if there might be a trend, but if we're not able to observe it with our current instrumentation, you won't see it plotted. Okay, so these are the maps and these are the global averages. And we see that near surface humidity has increased over both the land and the ocean. So you see very likely over lands, and oceans is likely because we don't have as many observations over the oceans. And when we go to relative humidity, so remember that relative humidity is the amount of water vapor in the atmosphere divided by the saturation water vapor. So it was like how much is it holding over how much could it hold? So here we see quite a different picture. We see a lot of brown, still a lot of X's, which means not significant trend, but a lot of brown. And particularly brown over land. And this means that relative humidity has very likely decreased. So notice the language, very likely decreased over land areas since 2000. And the reason is that the denominator, so the amount of water that the atmosphere can hold, is increasing. So that denominator is increasing faster than the amount of humidity that we're adding to the atmosphere. It depends very strongly on temperature. Okay, the next thing I want to talk about is observed precipitation. And here we see a very mixed picture in this map. We know that global land precipitation has likely increased since the 1950s, with faster increase since the 1980s, but there is medium confidence in this result. So, due to the sparsity of observations, etc., and also the heterogeneous trends over the globe, the signal is not as strong. And we're going to talk a little bit more about this. But in this graph here on the right, I'm showing you the change in precipitation per degree Celsius. So as you warm, how much does precip change? And if we're looking at mean precipitation, observations, which are in black, are telling us that it's between 1 and 2% per degree Celsius. However, as you get to more extreme precipitation, whether it's a 24-hour extreme or even extreme at shorter time scales, we see much larger increases. And we're going to talk about this a little bit later more, but notice that difference between mean and extreme. Now, because it's getting warmer, and because a warmer atmosphere has a higher capacity to hold water, you see that evapotranspiration has increased over the globe. And what I'm showing here, these are observations still, and these are ways that the models can attribute that change to either greenhouse gases or other things that would include, say, aerosols. And so here, this graph down here is how much of the observed change in evapotranspiration can we attribute to greenhouse gas forcing. Again, red is increase and blue is decrease. And you see, I mean, over the oceans, we have a very consistent picture with some patches, but we see higher evapotranspiration associated to warmer temperatures. Over land, the picture is not as clear. You do see large regions where evapotranspiration has decreased. And this is because you have a soil moisture limitation, right? So it's not only how much the atmosphere is requesting, it's also how much can the land provide to that atmosphere. So there's a soil moisture limitation for evapotranspiration. So then when we bring precipitation and evaporation together, P minus E, which would be similar to river runoff. So if you average this out, it should be very similar to river runoff. That's how much excess precipitation do we have once we take out evaporation over land. We see that basically there's very low confidence in trends. So we don't really have a clear signal as to what is going on in terms of P minus E or over land, over river runoff. So we don't really see a robust global trend for this quantity. However, as I said a little while ago, extreme precip behaves quite differently from mean precip. And we do see a very clear evidence that the frequency and intensity of heavy precipitation has likely increased at the global scale over the majority of land regions with good observational coverage. So that's key. So if you look at these dots where you have observations, they are definitely not all over the globe. But if we do have observations of extreme precip, most of the significant trends are positive. So if you look, this is a good graph to look at. They divide it by regions: global land, Asia, Africa, And if you the box on the left would show the positive increases, significantly positive increase, and negative. And it has to lie outside of this box and whisker plot for it to be significant. That is not by chance, just by chance. So the only observations that we see that are increasing beyond chance are the positive trends, the significant positive trends in extreme precipitation. So this is a much more robust result than the mean precipitation. Why? Because extreme precipitation scales is very much related to how much water is in the atmosphere. When you have a very heavy precipitation event, it tends just to rain out however much water is in the atmospheric column. And this is, you can kind of mathematically derive this, and it's about 7% increase in the water holding capacity of the atmosphere per degree Celsius, and extreme precip kind of scales at that rate. So let's go back to this plot that I showed you before. Changes in mean precipitation in observations, and this is also in models as we'll see later, are about 1 to 2% per degree Celsius, and there's a very heterogeneous pattern in space, whereas extreme precipitation increases at a rate of about 7% per degree Celsius, so much higher, because extreme precipitation depends on the amount of water in the atmosphere. But when you're talking about mean precipitation over the globe, there's other constraints that are related to radiation and how much the atmosphere can cool to remain in radiative balance. So there's just kind of different mechanisms that are constraining mean precip to much lower values than extreme precipitation. Okay, so based on observations, and please remember that this also depends on availability. We could potentially have more robust findings if we were able to fully observe the globe. But based on observations of the historical period, we are very confident that the temperature has increased. And we're quite confident about the fact that specific humidity has increased, that relative humidity has decreased, and the global evaporation has increased. Now, as I go to kind of orange and yellow colors, it's like we're not super confident in this. So we are quite confident that the frequency and intensity of extreme precipitation has increased. We're much less confident about precipitation. It has increased, but we have medium confidence, and we have pretty low confidence on P-E, the runoff, which would be the same as runoff on a global average over land areas. Okay, so very dark red is more confident and yellow is less confident about these results. Okay, so now let's move on to projections. What will the future hold? And to do this, we need models to be able to know what the future holds. There's a lot more uncertainty, right? Because now we're dealing with different possible scenarios, and then the models are imperfect representations of our system, but they are the only tool that we currently have to understand future climate. And in this assessment report, another new thing is that we are talking about SSPs. So the scenarios are SSPs, shared socioeconomic pathways, and they're narratives that are describing broad socioeconomic trends that could shape our future society, and they're intended to span a range of plausible futures. So if you are familiar with previous assessment reports, you used to have the RCPs in the fifth assessment report, which were exclusively dictating the radiative forcing that was going to be used in the models. And before that, there were the SRES. Now I'm not remembering what those stand for, but SRES were also kind of narrative-driven scenarios. the SSPs, are like a blend of the narrative plus the radiative forcing. So when you see them, they'll range from SSP1, which is like the best possible world where we have economic growth, but you have less fossil fuel intensive economies, all the way to SSP5, which is also a world in which we have strong economic growth. However, that growth is really strongly based on fossil fuel consumption. So in terms of kind of humanity, SSP1 would be the best. SSP5 is actually kind of the second best if it weren't for the huge climate impacts that it has. But in terms of like education, GDP, healthcare, it's kind of a really good world, but a fossil fuel world. And then these middle ones, especially SSP3, is based on like regional rivalries, lack of funding for healthcare and education, and fossil fuel intensive. So these are possible futures that we can see. I like this graph because here it's kind of a depiction of the temperatures in the historical period as of 2020, and then you kind of increase as you move into the future, and the rate at which you increase depends on what future we decide as a society, what path we decide as a society. Okay, so these SSPs, shared socioeconomic pathways, SSP 1 to 5, have a range of possible futures. I like this graph because you have the climate stripes, and then you have the futures, right? Like from kind of the best possible scenario to the worst. Notice, we are not going back to a cooler world, right? Every scenario is warmer than what we've experienced in the past. And that's because CO2 has a very long lifetime in the atmosphere, from 100 to 1,000 years or more. So we are already committed to this warming. Then the question is, how much more will we have? Okay, but just, I guess this graph for me is very telling in terms of we already committed to a warmer world. Give me 1 second. No. So another thing that I want to say is that in some of these scenarios, you have a peak on the CO2 emissions and then it goes down. So here SSP2 would be, I think it's like 2030 or something like that. SSP5 has it really late in the century. For SSP1, it's right now. It's indicating that we should already have been in a downward trajectory. So evidently we're not there yet. And yeah, so that's what I wanted to say. Okay, one other new thing about the IPCC report is that they have information based on warming levels. So some of the graphs that you'll see are based on warming levels. So regardless of what emission scenario we're talking about, or what future time period we're talking about, they'll report things based on how much warming the particular simulation has seen. So let me try to explain this. So let's imagine you have a run. This is just an example with several simulations with the SSP1 to 6 scenario and with the SSP3 7.0 scenario. Okay, so this orange ones are a very intense scenario, and these are a much kind of greener world scenario. And most of them will hit well, they will, yeah, the vast majority will hit 1.5, except maybe some of these simulations that didn't hit it. But each individual simulation will hit 1.5 or 2 or 4 at a different moment in time. So what the levels are is for each individual simulation, they'll let it run. And then it hits, let's say here, it hit 2 degrees in 2020. And so they'll average that plus the projections of all these other models at the moment that they hit 2 degrees above pre-industrial. And then they'll average it out and they'll see, regardless of the scenario or the moment that they hit 2 degrees above pre-industrial, what does that spatial pattern look like? So what you can find from that are robust projected geographical patterns of any variable. Here I'm showing temperature, precip, and soil moisture that can be that you can see regardless of, independent of the timing at which they reached 2. So usually we'll have 1.5, 2 or 4. Sometimes you'll also see 1.7. Okay, so this is new. This they didn't used to do this in the previous IPCC reports. They would just say, okay, all the models that are forced with the high emission scenario, what is your projections as to what will happen in 2100? And so you would see kind of the differences between a very warm scenario and a very and a less fossil fuel intensive scenario in the future, whereas here they're all treated the same, and you're just kind of looking at what the world will look like when you hit these milestones of warming. The report also has the other ones, but this is pretty new, the global warming level. So I wanted to take a little bit of time to explain to you what you're looking at when you see the warming levels. Okay, so without large-scale reduction in greenhouse gas emissions, global warming is projected to cause substantial changes in the water cycle at both global and regional scales with high confidence. And again, I'm starting with temperature. So annual, so this would be the warming level for 1.5, for 2, and 4. And we see basically an amplification of this pattern that we're already seeing with observations. The more we warm, the hotter the land is, and also you have hotter land than the ocean, and you have much more warming in the high latitudes, in the Arctic and also in Antarctica. In terms of precipitation, what we see in general is that places that have traditionally been wet will be wetter, and places that have traditionally been, in the historical period, been dry, they'll get drier, and the pattern just amplifies with different levels of warming. So precipitation is projected to increase over the high latitude. So regions like Illinois will likely see higher mean precipitation. And also in the equatorial Pacific and some monsoon regions, but it'll decrease significantly in parts of the subtropics and some areas of the tropics. So Central America, again, Central America, and then the Mediterranean, Northern Africa, these keep on appearing as places that are going to see decreased precipitation. And of course, this affects soil moisture, right? So in general, we see that soil moisture follows the precip. However, you also have the effect of evapotranspiration. So to me, I think something that I had not seen in previous IPCC reports was this kind of very concerning pattern over the Amazon region that is emerging pretty robustly in the sixth assessment report. Yeah, and essentially, so here you see the Western US also experiencing significant drying. And again, let's just pray that we never get to this 4-degree warming world. I think this is more will be in the 2-degree warming world. Okay. Now let's go more to extremes. The sixth assessment report, the models, the CMIP6 projections, you have more drier days. You have more drier days. So here in general, the number of dry days, dry days per year increases as you go to stronger and stronger scenarios. So this would be the 126 to the 585, and anything red means that you have longer and longer periods without rain. So you're seeing all these regions that have more prolonged dry periods. Please note that if you see the hatch, it means that there's low model agreement. So only where the color is solid do the models agree. Now look at what happens for daily precipitation intensity. So more intense precipitation is expected to fall in any particular storm over almost all land areas, and this is very likely. So intense precipitation is projected to intensify at a rate close to 7% per degree Celsius of warming. There are spatial differences though. And again, so I'm sorry, this is the third time I showed this one, but water cycle variability and extremes are projected to increase faster than average changes in most regions of the world and under all emission scenarios with high confidence. So before I was showing you observations of extreme precipitation. So the black again is observations, but notice that the GCMs are also indicating a much stronger change in 24 hour, the orange would be the 24 hour, the GCMs, and you're seeing much stronger changes in extreme precipitation than in mean. This is another way to say that. Now we're looking at a 10-year event, a 50-year event. So 10-year events are in purple and 50-year events are in orange. And the level of warming is in the x-axis. So a 2-degree warming world would mean that the increase in the intensity of this event is on the order of, about 14. So it sort of scales as 7% per degree Celsius, essentially. And this is very similar information than this one. Than this one, but looking at it as a map for different warming levels. So you again see, in contrast to what we see with precipitation, where we have some regions that are average are going to get drier. If we're only looking at the annual maximum daily precipitation, so extreme events, they are projected to increase over most regions of the world. And so that means that even regions like the southwestern United States that are going to see longer periods of longer dry periods, when it rains, it's going to rain more intensely. So this is the projections for those drier regions. And in terms of evaporation, it is virtually certain that we'll have more evaporative demand because we're in a warmer atmosphere. And the models project an increase in evapotranspiration over most land or areas. However, of course, there are regional differences because they're influenced by soil moisture changes and vegetation, which will modulate that flux into the atmosphere. So here we're seeing December, January, February, June, July, August evapotranspiration trends, percent changes, and red is higher and blue is lower. And you just see kind of over the oceans, this is pretty certain. And then over the land, you have more evaporative demand, but some regions have constraints. And kind of let's get this whole picture. So consistent with this warming world, you have increases in vapor pressure deficit. So everything you see here is brown. It says, you know, you're going to have more vapor pressure deficit. So brown is here. And then that leads into more evaporative demand. And in many regions of the world, this will result in decreased soil moisture. This is soil moisture in the top 10 centimeters and in the total column. So you do see agreement in some regions, especially if you go to the higher emission scenarios. So the higher emission scenarios are just kind of putting a bigger hammer on the system. So you do see kind of amplification of these patterns that are quite muted if you go to less intense scenarios. And then now let's go into runoff. And here, take this with a grain of salt. There's a lot of hatching, which means that there's a very low model agreement. So runoff is one of those variables that, we have to be just very careful with. But in general, runoff increases in most parts of the northern high latitudes because they're just projected to be wetter, in eastern North Africa, and decrease in the Mediterranean region, southern Africa, southern Australia, and in parts of Western Africa, and Central America and parts of South America. Okay, so just kind of to wrap things up here, projected changes in hydrologic extremes are larger in frequency and intensity with every additional increment of global warming. And I like this graph because it's very intuitive. The first kind of these dots represent frequency. So in the historical period, if you have a heavy precipitation event, a 10-year event that would occur once every 10 years, as you go to warmer scenarios, so at the 1.5, it'll be 1.5 times as likely. Then here it's 1.7, then here it's 2.7 times. So as you warm, it'll be more likely. And then in terms of intensity, it'll range between 6.7 times wetter, this one, 10.5 times wetter, which is at the 1.5 level, and then all the way to 30% wetter at the 4 degrees. And a similar thing happens in terms of agricultural and ecological droughts, where the 10-year events will occur more frequently and where the intensity will be stronger the more you go into a warmer world. So to conclude, I like to kind of take a step back. We talk a lot about mitigation, which is to prevent or reduce the emission of greenhouse gases into the atmosphere. So we talk about sustainable transportation or clean energy, etc. The other part of the coin is adaptation, adjusting to what we already committed to and future changes. And I like this quote that I heard last semester by Dr. Adil Najam, who's the president of the World Wildlife Fund. It says, mitigation is to carbon as adaptation is to water. So very likely the effects that we're going to feel as a society by climate change will be related to water. So this is a world that we need to be prepared to live in and take adaptive action to protect vulnerable communities. And with that, I will open it up for questions.
All right, thank you so much. If you can see, we do have a poll up there, but one of the questions that we've gotten so far, and again, what questions you have, you can put in the chat box and we'll go from there. But the first question we have, are there data that compare and contrast population data population data size and changes globally with temperature?
Okay, I'm not 100% sure I understand. I guess, okay, so
So they're
population
comparing population data to temperature globally. Is there any correlation, I guess, between that?
that places with higher populations would experience a different
Well, either that or as maybe even as population changes, as it increases or decreases. And if that's not the right intent, then if someone wants to put that back in the chat, that's fine. But I'm thinking that's what they were looking at.
So I'll respond in two different ways. Hopefully I'll hit the question. So one issue. Okay, so in terms of the impacts of climate change, um, the impacts are felt disproportionately in vulnerable populations in the developing countries. And if you're talking about impacts such as heat extremes, uh, definitely you have areas in Africa and in India that are going to be very hard hit by current and future heat extremes. Um, so that's one part of it. And also, if you are in a densely populated area, you also have additional impacts due to like urban heat island effect that compounds on climate change, global climate change. So there's also regional impacts that are very important. So that might be an answer to the question. And if not, I'll be happy to kind of shift and answer it. Yeah.
I think this person is clarifying a little bit more. It says if the world population drops significantly,
Oh, yeah.
will there be an impact? Is the
Yes,
data
yes.
assuming the
Okay.
status quo on increases in population?
Correct. Okay. Yeah. So now I understand better. So SSPs, so those scenarios, population is a super important part of how they're built. So if you look at an SSP1 scenario, it is very much dependent on a decreasing population because okay, so CO2 emissions scale with GDP. GDP scales with population. So population is a super, super important part of how the SSPs are built. So they're in there, all this population data and differential population changes between different countries are built into the SSPs. I think that hit the question.
Okay. Another question. Are there documents, websites, etc., that present this information for non-scientists and the public? It's hard to describe models being reliable to many people.
Yeah. Okay. So so from the IPCC, the best resource would be the summary for policymakers. So that is the one that is written for a lay audience and that is actually used for policy in many parts of the world. So that one would be the best resource. There are other resources. So I'm going to plug the Project Drawdown. I'm going to write it here. And Project Drawdown is if you are interested in mitigation strategies or just kind of a 101 to climate change, Project Drawdown is really an excellent resource. So I highly recommend that one. I use it a lot when I teach my own classes.
Is that a website or is it a book or?
So it's a website. They have a book. They have modules for education. So if you just Google Project Drawdown, you can find just really fantastic information. It's primarily related to mitigation. So like what are the types of changes that we can make to really bring down CO2 emissions?
Well, there's another question. Name of one for policymakers, but I think you've already mentioned that.
Yeah, so yeah.
Or is there a particular name for that one other than just summary
So
for policymakers?
that would be the one related to the IPCC report, and the
Mm-hmm.
IPCC is like the most trusted
Mm-hmm.
resource. So if for policymakers, it would be the SPM, the summary for policymakers.
Okay. Well, while we're waiting for other potential questions, I have one. So in
Yeah,
terms of runoff, so we've got these likelihood of heavier, more extreme precipitation events.
yeah,
But then we've also got the additional evapotranspiration potential.
yeah,
So I guess what we're looking at potentially in the Midwest is um, these heavier precipitation events, but then more potential for things like flash droughts in between, where we've got these what precipitation was there in terms of soil moisture going up um, into the atmosphere, and then soil moisture drying out in between these heavier precipitation events.
yeah. And there's also one more factor with which is how the ability of the soil to infiltrate changes if you're increasing the number of dry days in between. So that also changes. That's why runoff is such a difficult variable to predict. There's just so much uncertainty related to it. Yeah, so I honestly just don't have a great answer. I don't think
Mm-hmm.
we have we there's just too much uncertainty right now as to both the observations and the projections.
And then one other question I have too is in terms of soil moisture, do the models take into account what changes may be taking place with organic matter, soil organic matter?
So I guess in a rudimentary way, so when you look at Earth system models, about half of them have pretty sophisticated biogeochemistry. So one of my colleagues here, Atul Jain, works significantly on biogeochemistry. So to the extent that the representation of the biogeochemical cycle is accurate, that's what it would incorporate.
Okay.
Yeah.
Okay.
And there is pretty sophisticated hydrology in a lot of these models, but still just a lot of uncertainty remains.
Mm-hmm.
And I think you saw that like we have very, very high robustness and certainty about temperature. And as you go kind of down into more complex and interconnected things, the uncertainty just blows up.
All right. Are there other questions anybody has? Francina, thank you so much for all of this information.
Yep,
Um,
you're welcome.
do you, if people had questions at a later date,
Oh,
do you
sure.
have an
Yeah, and
email that you?
I can also give you guys this presentation if you want. And yeah,
Okay.
and you can email me um, whatever questions you have, and if I know how to answer them, I will.
And this, with this recording, we will get this up and have it in our extension YouTube channel. It'll probably be several weeks before that happens, but we'll send out a notice to all registrants when it is available.
Okay.
So again, thank you all so much. Just to let you know, our next session will be on June 27th at 1 p.m. And we will be sending out information on that in terms of speaker and topic in the next few weeks. So or at least within by early May. So with that, thank you everyone. Again, thank you, Francina, and we will let everyone go. Have a good
Thank you.
afternoon.
Bye-bye.